Hello. So we'll go to looking at the code editor we'll be using for this program, and it's going to be Chrome Dev Tool. So if you don't have Chrome, I will advise you download it and install. It's very easy to download. So just install it on your Mac or your Windows. So I'm using Mac, but it's the same process to get your Dev Tool on Chrome. So the first process is you right click and inspect, right? Right click and you inspect. You're going to have your Dev Tool. This is the Dev Tool. Then the second process is if in your Mac you right click and you are not seeing inspect, then you should look at this three dots here. You click on it. I think the same process too does the same with Windows. So you come here, more tools. So you come to these more tools, and then you look at developer tool. Just click on this developer tool, and it's going to come up. So by default, elements will show or console. The highlights might be either elements or console. So, but this tool is not actually what we'll be looking at. We'll be going to sources, but then before sources, so if this opens just as mine is open at the bottom, or yours open by the side, it could open either way, either by the bottom or by the side like this, right? So what you just do is to hit either of these three dots, you hit here, but what we want is to open in another window, because we're going to be writing our code, so we could have enough space, right, for it. So you're going to click here and then open in another window. So that is exactly what we want. So I can just make this to cover the whole screen. Yeah, so this is console. Where we're going is sources. So go to sources, and this is actually where, so yours might open on pages or workspace. So if that be the case, good. You might see something like this, and maybe you are seeing pages, something like that, or something. So what you don't need to do is to click these two arrows and click on snippet, right? And you can just enlarge it. So you go to snippet, right? It should be on snippet. And what we're going to do now is to create new snippet. So this is where, so let me just create a new snippet. I will click this, I will put new, I'll name it new for the purpose of just testing. And here we'll be running all our codes on this data structure and algorithm course, right? So we'll be writing our code here. And then once you finish writing your code here, you look at here, you can see this button here, then you can run your code, right? So this is one of the ways you can run it. Then another way is to right click and then you say run. Good. So these are the two ways you can run your code. So I have a code that I'll just copy. I'll just copy quite a simple code, just hello world code, a function for us to just see how you can run. Then for you to clear your console, you just click here. It will clear the console. So let's run this function here, and you see the result. So once we run this function, we're going to get this hello world, and here you see we've gotten our hello world. So that's actually, you can still just right click as I said earlier and then run. So we got our hello world, and here you can clear the console. You hit again, it runs, right? So this is going to be our code editor for this course. Thank you very much. See you on the main program. Thank you. It is very, very important that we understand big O notation as we embark on this journey, because this is going to really help you and make you a better programmer. That's your next trick. So the best way I can explain this is with these diagrams that I brought here. So let's assume that we have code A that runs in less time. So let's assume that this code runs for 15 seconds, right? So perhaps this code, we just put that it runs for 15 seconds. That's code. Code A now runs for 15 seconds, right? And we have code B that takes more time to run. And then when you run code B, it runs for 60 seconds, right? So code B runs for 60 seconds. I'll say that code B runs for 60 seconds, right? So now the understanding is that if you're working with time, this code is better. Why? It's faster. But if you're now working with space, let's not assume that code A runs faster, but then takes more space. So code A takes a whole lot of space when it's running. Let's assume that this is the space that it takes. Code A takes all of this space to run. And then when you look at code B runs for 60 seconds, but takes this much space, right? But then it runs for 60 seconds. So we could say that code B takes less space. So when you look at code A and code B, you can see that in code A, this lays more emphasis. In code A, could A lays more emphasis on time because it's faster with time, right? So we could say that this is time complexity. While when you look at could B is laying more emphasis on space. The space is less, but then it takes more time to run. So we could say that this is space complexity, right? So the choice is yours, which you want to say is better. It depends on what you want. So if you're looking at a code that you want actually to run faster without actually giving more emphasis on the space, then we could say code A is better. But if you are looking at a code that you are not laying more emphasis on the time, but then you are laying more emphasis on the space, right? Then we could say that code B is better. So this is what we'll be dealing with in big O notation, right? So we'll be looking at measuring the big O, looking at the worst case, which is the big O, right? So let's assume we want to iterate through this array to find a certain number, and we're actually looking at the number 1. So if we want to get the number 1, you know that 1 is going to be our best case because that is going to give us the least number of iteration, right? So we'll say that 1 is the best case, right? And then if you look at it again, go through this array, you see that 3 is the average case. So we could point this arrow and say that 3 is the average case. And then 5, of course, is going to be our worst case. And now this best case is designated with omega. And the average case is designated with theta. While the worst case is designated with omicron, which is the big O. And that's actually what we'll be looking at, right? The big O. So when we talk about the big O, always have it in mind that the big O is always the worst case. So that's what we'll be looking at, right? I just want to clarify that before we move on. Thank you very much. So we're going to start with O of n. And the reason why we're starting with O of n is because, in my opinion, I feel that O of n is easier to grasp. So we are going to start with that. And I've created a snippet here, a new snippet, and I named it O of n. So all you don't need to do is to create your snippet, this new snippet there, and you can name it O of n or whatever you want to name it. So let me remove this because I don't need it. So for me to explain this O of n, I'm going to write a function. And the function, I will name the function a number. So I will name it num, which stands for number, and with the parameter of n, right? So I've just created a function here, which has a number of n with a parameter, which has a name of number with a parameter of n. So what we're going to do is that we're going to run a for loop, and the for loop is going to run n times. And this is how we do it. We're going to say for I is equal 0. I will explain all of this. Then I is less than or equal to n, because we want to run it n times. Then we increment I. And here we're going to say console.log I. Good. With this, we succeeded in creating a for loop that runs n time, right? So once we call this this function, because for the function to run, we have to call it. Any value we put here is the amount of time n is going to run. So let's say we put 3 here, right? And then let's run our code. Now, you could see the output. We have 0. Why do we have 0? Because we say I is equal to 0. If we change this now to say I is equal to 1, and then let's clear this, and then run, it's going to start from 1. But of course, we want I to start from 0, right? So we'll clear this up. Now, let me go back to what I was trying to explain. Now, we have 0, 1, 2, all through to 3. We are having 3 because I say I is less than or equal to n. If I said I is less than n, then we would have 0 to 2, right? So if we now come here and put 5, and then change this to 1 for clarity's sake, so that I will start from 1, right? So when we run this, let me clear this out. When we run this, we're going to have 5, 1 to 5, right? So what does that tell you? That the number of operation is proportional to n. That is that as n increases, the number of operation increases. Now let's put 10 here, and let's clear this out. we run this, you see the number of operation has also increased to 10. So when you look at the graph of O of n, let's look at the graph here. This is exactly how the graph looks like. You see, the graph is a straight line graph. Straight line graph, O of n. So as the number of n increases, the number of operation increases. You can see it from the graph, right? So this is how O of n works, right? Going further, I want to explain constant in O of n. So let's say we have two functions, two loops, sorry, here in this function, and we call this j. So let's change this to j, and the console j. Now, if we put n to the 3, look at what's going to happen here. We run, you see that there's a repetition. So this, the first 1 to 3 is for this, and then the second 1 to 3 is for this, right? So one could say that we're having O of n plus n, right? Which will give us something like this, O of 2n, right? Because, let me clear this. Because what we're having here is n plus n, which is 2n. So this constant is actually dropped. Now, we don't really care how many loop that we have here. Whether it's going to be 1, it's 2, or it's 10, it's 50, it's 100, it doesn't really matter. What matters is that what we are running here is that as n increases, the number of operation increases, which is O of n. So this constant is dropped. Always take note of that. The constant is always dropped. So there's nothing like O of 2n, O of 10n, O of 100n. No, that constant is dropped. So what we have is O of n. It doesn't really matter the number of loop that we have at the end of the day. What we are looking at is, so long that the number of operation increases or decreases as n increases or decreases, then what we have is O of n. I hope that is clear. So that's it for O of n. Thank you very much. And then please take note that this is not part of the equation. This is just, let me comment it. This is just for explanatory sake, right? Thank you. So we'll be looking at O of n squared. And let's go to our O of n and copy this code. So we'll bring it here. Now what we're going to do is we'll cut this and then remove this console.log here. And now drop the second for loop inside the first for loop. So this is called nested loop, right? So now what we'll now do is that we'll call I and j together. Just take note of what you're going to see here. So if you look at this now, you see that this, the first for loop, we have two for loops here. One is nested into the other. So we're going to run this now. And when we run this, you see that the code ran 9 times. 1 to 3, which is 3. Then another 1 to 3 again, which is 6. And then another 1 to 3, which is 9. So the operation 9 times. The operation was carried out 9 times, right? So if we put, say, 4 here, 4 and run, let me clear this, run, you're going to see that the operation was carried out 16 times. Now, so let's count. The first run, first to 4, then another 1 to 4 again, which is 8, another 1 to 4 again, which is 12, and another 1 to 4 again, which is 16, right? So the operation was carried out 16 times. And if we put 5 here, I'm trying to drive a point here, so just follow me. If we put 5 here, let's see how many times we got here. You're going to see 1 to 5, another 1 to 5, which is 10, another 1 to 5, which is 15, another 1 to 5, 20, and then 25. What does that tell you? That tells you that this operation is being carried out on square of whatsoever number you put here, whatsoever figure or value that n is. So whatsoever value you have here, the operation carries out on the square of that value. So if you look at what we have here, let me comment this. What we have here is going to be n times n, which is equal to n square, right? N square. And that's exactly what is happening here. So whatsoever we put here as n, right, your number of operation, what happens is that it squares it. 5 square is 25. we first of all ran 3. 3 square is 9. And the operation, we had 9 operation. When we put 4, 4 square is 16. And we had 16 operation. Here we put 5. 5 square is 25. We have 25 operation. And so on. So whatever number you put here, just the square of it is the number of operation you're going to have. And when we have such scenario, we say it is O of n square. And let me show you the diagram, how the diagram looks like. So this is the graph of O of n square. Now you can see that n is 5, while the number of operation is 25. When n is 10, the number of operation is 100, and that is how it increases like that. So usually the number of operation is square of whatever n is, as we've seen here, right? So let's look at it in comparison with O of n. And when you look at both of them, O of n and O of n square, you see that O of n is a better code than O of n square. So these are things you just have to take note of when you're writing your code as a programmer, right? So when you have opportunity, you have a situation where you have to write a code, a nested for loop, or which will give you O of n square. And you also look at it that, okay, same situation, I can still write this code on O of n and it will run and give me better results. So you just know that you have to choose this over this, because this gives a better result, right? So these are a few things you just have to take note as a programmer, right? And then just as we discussed on O of n, whenever you come across a situation where you have a constant, of course the constant should be dropped, right? Yeah, I think that will be all for O of n square for now. Thank you very much. So we'll be looking at O of 1 today. As you can see, that is already in our snippet. And this is a function, a very simple function here, add value, and with a parameter n, which we are returning. Let me remove this first. We're returning n plus n. And for the fact that we're returning n plus n, this is just an addition, right? So for the fact that we have a very simple addition, this is O of 1. And this is just how it is. So even if we have another addition here, say plus n, you know, continuous plus another n, right? And if you look at this now, you would want to say that maybe this is O of 3, right? But unfortunately, we don't. The constant is usually dropped. What we have is O of n. But considering, so what we're actually looking at is the operation that is being carried out, right? Not the number of n that we have here. The operation is addition, simple addition. You know, n plus n plus n plus n and all that is O of 1. And when you look at the graph here, you see that the graph is a straight horizontal line, as you can see the O of 1 graph here, and it is regarded as the most efficient when you compare it with O of n, of course. And you could see it here that the function is quite a very simple addition, n plus n. So that is all for O of 1. It's very, very simple and efficient. So we're going to look at O of log n, and in order to do that, I would like us to look at this diagram, because we'll be using this diagram to, not really diagram, but this array to explain this O of log n. So imagine that we have to sort an array of say 1 to 100, right? And we are to pick a particular number from this array. Normally, what we should do is to iterate through this number until we actually get to what we are looking for, right? So we'll go through it step by step, and that will be usually O of n, if you'll be following, right? So that is the process. We'll iterate through step by step. We'll go through each number, you know, one after the other until we get to the number we are looking for. But now, imagine that we have hundreds of millions in our database. You know, imagine that we have billion information, and we are to get a particular, sorry, this should be O, not n. And we're just looking for a particular value from all the billions of information or hundreds of millions of information in our database. How are we going to go through it? And we know how O of n works, that the number of operation is proportional to n. So as n increases, the number of operation increases. So imagine that you have over 200 million information on your data. It means that the number of operation is going to increase when you're using O of n, and that is actually going to slow you down and then be a big issue to the database. So in such a scenario, this O of n is not actually going to work, right? So we have a better way of doing that, which is by searching by what we call the binary search. And how does it work? The binary search is that you just have to, assuming that we have to go through a scenario. So I brought out an array of number 1 to 16 just for explanatory sake. So assuming we are to pick a particular number, assuming 1, right? So let me just, assuming that we are to pick this number 1 from this array, you get, and we are to use binary search. How are we going to do that? The solution or the pattern for binary search is that you divide from the middle. So first of all, okay, what we have to do is we have 16 numbers here. So we go through this array and divide from the middle. So we separate this. So let's just separate this. Now we have, take cognizance of the amount of operation we're taking here. The first operation is that we divide from 16, we divide into 2. Now, is 1 on this side or the right hand side? No. Is 1 on this side? Yes. So we throw away this. We put this off. So we just remove it. Now, so the operation, we've got 1 operation here. Now from this 8, we divide again from the middle, right? Now we now have left and right. Is 1 on the right? No. 1 on the left? Yes. So we remove this. How many operations now? 2. We have 2 operations that we've carried, right? And then we divide again. We divide again. We shift. How many do we have now? We have 2 again, 2 sides, right and left. Is 1 on the right? No. Is 1 on the left? Yes. So this, we discard it. We don't need it. And this is the third operation. Third operation. Now we move again. We divide by at the center again. We now have 2 different, right and left. Is 1 on the right? No. Is 1 on the left? Yes. And now we don't need this. How many operations? 4. So we discard this. So we've carried out 4 operations. And this is exactly what O of log n does, is, right? Now imagine that we are doing this on O of n. Do you know how many operations would have carried? 16 operations. Check it with 4 operations. Which is more better, right? Now, this 4 operation, remember that the number of array is 16, which is what we have here. Let me remove this. So the number of operation is 16, right? And we carried out 4 operations. And we're doing it, dividing it by 2. Each time we divide by 2. Each time we divide by 2. So what we are saying here is this is just exact same as 2 raised to power 4, which gives us 16. So the same thing. So what we are saying is how many times can you actually multiply 2 to give you the total number of array we have? Remember, we have 16 elements in our array, right? So how many number can 2 multiply itself to give you that value that we're having? So for the fact that we have 16, 2 can multiply itself into 4 places, which is 2 raised to power 4 to give us 16. And then when you convert it to logarithm, this actually gives you log base 2 of 16. And of course, if you understand how log works, log base 2, and when you are asked to look for log base 2 of 16, what are they telling you? What they are just telling you is how many times, what power can be raised to 2 to give you 16. That's what they are asking you. That's logarithm for you. So what power can be raised to 2 to give us 16? And that power, what can be raised to 2 to give us 16 is 4. So when you have data that is huge and you have to iterate through the array, so you have to realize that O of n, once the data is huge, O of n will not actually be effective at that moment. The best way you can search through the array is binary search, which is O of log n. So that is actually where O of log n comes in. And we'll write it here, O of log n. So when we actually begin to write our code, all of this information, all of these we've been learning will become very, very easier to grasp. So let's look at the diagram of O log n to see how it looks like. So you can see the diagram, O log n. So from looking at the diagram, you could see that this is more efficient than O n, right? O of n. So our O of n moves straight. Why O log n is going this way, right? So this is far more efficient, especially when the data is huge, right? Thank you very much. This is it for O log n. Bye. Now we are on linked list. And we have the list of our nodes here. On linked list, unlike array where you have index, the linked list does not have index. And there's something that happens on linked list. Each of the linked lists has a head and a tail. So the first on the list is actually the head. So we're going to bring this head and say this is the head. while the last is reference or is called the tail, right? So we're going to say this is the tail. And then the tail, which is the last on the list, or before then, each of these actually called a node. Take note of that. Each of these are called a node, right? And each of the nodes points to each other. They have an arrow pointing to each other, right? So the first node is the head, and the last node is the tail, with each of the nodes pointing to each other. While the last node has an arrow pointing to null, nothing. It's pointing to nothing. So the head points to the next node, while the next node points to the next node until it gets to the tail, and the tail points to nothing. Take note of that. The last node, the tail, points to nothing. Now, in a situation where we have only one node like this, so what is going to happen? In a situation like this, we're going to have the head pointing to that node. So let me just, put it this way. So we have the head pointing to the node and the tail also pointing to the same node. All of them are going to point to the same node. Sorry. So they're all going to point to the same node. So this is a situation where we have just one node, right? The head points to the same node and the tail points to the same node. So please take note of this. It's very, very important because we're going to start writing our data structure in a moment, right? Thank you very much. So we're going to start our linked list code right now. So we'll start writing code on linked list. But the first thing is we're going to look at our node structure, right? Because we have to create a node for us to actually start writing our code. And I'll start with this example on this diagram. This is the diagram we had before. So remember that this is a node, right? And if we have only one node, as I explained before, both the head and the tail will be pointing to the same node, right? So that's exactly what we're going to do right now, right? Both of them are going to be pointing to this same node, while at the same point, the same head, which is now the head and the tail, will point to a null because it's a single node, right? So that's what we'll have to do now. So we'll say class, call this a node. Sorry. Then we're going to have our constructor with a parameter of data or value, whichever. So I'm using data. Now, what we're going to do is that we'll say this dot data is equal data, which is the parameter that I have their data, right? So that's the first thing. Now, we'll now say that this dot next, because there's always a next, right? So when you get to a tail, the next becomes, let me shift this. Yeah, sorry. So when you get to the tail, the next leads to null. So we'll now say this dot next is equal null. Why is that? Because we're having just one node here, right? Please take note of that. So this code here is actually what is going to create our node for us, right? So the next one now is now for us to have our linked list class. So we say class linked list, and then we have our constructor with the parameter of data. Then what we'll now do is to instantiate this node here. So we're going to say we're going to get an instance of this node, of course, which I will now call it my new node, or new node rather. This is equal to new node, which is this node. So I'm having an instance of this node, right? So that once this node has created a node for us, so that once this node has been created, we can now use it here. I think that's the right point. Yeah, so with data. Now that the node has been created, we'll now drop our linked list. We point our head, the head now to this node, just as you're seeing on this diagram now. And for us to do that, all we now need to do is to say this dot head is equal new node, the new node we have just created. Now that is not all. If you check it, you see that tail is also pointing to the same node, right? Because we have just one node at this point. So we're going to say this dot tail is equal new node. This should have been capital, sorry. This should have been small letter, sorry, not capital letter. So we'll change this to small letter and this to small letter. Good. We want to take count of the length. So we'll say this dot length. At this initial stage is 0, so there's nothing. Now, this is our node structure, right? So if for any reason now, I create a node as we've seen here now, right? Once I create this node now I can now create a node. Once I create this node now and run it, you're going to see the node that I've created here. So, and that is exactly what we're going to do now. So I'm going to say, now say let's my new linked list equal. So what I'm doing now is that I'm creating an instance of this linked list, right? So let my new linked list equal new linked list. That's it. And then I can console.log my new linked list. Good. So as you've seen on this diagram here, what we've done is that the node is 3. So let's just put 3 here and run it. We've got a single node here. So now I'll run it and let's see what we're going to get. Okay, so for the sake of the structure, the node structure, we put our length here to be 0. But now we are having a node. I'm just doing this for example. Of course, this length is going to remain 0. Once we are now writing our data structure, we will automatically be incrementing it, right? So, but for the record, let's just put this to be 1 because we have one node here. Then I think linked list. Oh, sorry, this should be not linked list. This should be linked list. Good. So let's run now and see what we're going to get. Perfect. So when you dropped it, you see that the data is 3 as to what we put here, just as we've seen on this image. So please let me remove this so that I don't get you confused. This is not part of it. Or let me just shift it down because I'm going to use it later. Good. So we have just one node here, which you could see that the data is 3. And next, that's the point I want to make now. Because we're having one node, the next is pointing to null. Now let's look at, let me raise this. Let me raise this everywhere. Let's look at the head. You could see that we have our data to be 3. Next is pointing to null. Now let's look at the tail too. The same thing is going to happen on the tail because remember that both head and tail are pointing to the same node. If you look at the tail too, you see that our data is 3. Next is also pointing to null. So that is actually how it is. So the next one we're going to treat now, we're going to write real data structure code. Thank you very much for this. Bye. So we'll be looking at push on our linked list, and we're going to write our code here as usual. So let's come here and copy what we have here and then put here. So for the record, I want us to change whatever we have here to value because it's most popularly used. So let's use it. So change every data to value and change this one too. I think that will be all for data. Good. So here we've already gotten our class component for the node, and here for the fact that when we are actually working on this, we had a node, so we had to hard code some things here. So let's just normally, because we're hard coding a node, we're trying to create a node, we instantiated this node component, class component here. So now we want to get our class linked list component. So we'll initialize this dot head to null and this dot tail to null. And then, of course, we have to hard code the length too. So these are the node class component and the linked list class component. There's nothing here, so this dot head has been set to null. This dot tail set to null. So at this initial stage, everything is 0. Nothing is existing, right? So as we now keep pushing node inside the linked list, we'll start creating and removing, right? So the first thing we want to do is to actually push a node. So we're going to write our code to see how a node can be pushed into an existing linked list, right? So we're going to have our push method here. So we'll say push. And of course, our parameter is going to be value. And no, I think this push method should be written inside the linked list. Yeah, not I think. That is what we're going to do. That's the right thing. So because we'll be referencing the linked list, right? So for that reason, we'll be doing this. Good. I know you are going to ask why. Why should the push method be written inside the linked list, right? And we have the node on its own. So let me explain. Let me actually throw more light to this. So this node class component is actually used to create a node for us. I think I've stated that when we're talking about the node, creating a node structure. So this is the class component that creates a node for us. Now, when we are done creating this node, we need to be able to manage this node, right? We should be able to define the operation that goes on inside this node, right? So we can literally say that this linked list component is actually modifying all of these that are here, the head, the tail, and the length. So what do I mean by modifying them? You can see here now that they are null, right? At the point where this node creates a new node, this head changes from null to the new node, right? That we already have, which is the node dot value. So let's assume this now. You can see exactly this what we're talking about now. So is this linked list? Remember that this is a linked list. This what we have here. This is not an array. Of course, we already know that we are on linked list. So this is a linked list, and this is actually what modifies this node that's been created. These are nodes that have been created. So this linked list is what modifies all this. It's okay. This head now has changed from null to 2. So we already have our node dot value equal to node dot value is this is the value inside the node, right? So when we're talking about the node, we're talking about just this entity. Now when we're talking about the node dot value, we're talking about all of these, both the 2 and the node inside. So this now has been modified from null to 2, and you can see the tail. This also has modified this null, the tail null that is not here, from null to 5. So it has changed it from null to 5. And you can see the length. Length is equal to length is 0, right? But if you look at this now, it's going to be modified. We'll have how many lengths here? 1, 2, 3, 4. So this length is going to be 4. So this is actually what modifies everything that whatsoever that we've created from this class, the node class component, right? So that is why all our method, the push method, the pop, and all that, all the method we're going to work, they are all going to be inside this linked list class component, right? So that is the reason why the method will be treating going forward will be written inside the class component. But when we will be handling questions, the data structure and algorithm questions, we literally are not going to be using this class component, because if you go to most of your interview questions are not going to be referencing the class component, right? So in that stage, I'm purposely going to remove this class component, and then we'll use a function, right? So in situation like that, we'll no longer be using this dot head. But you see, it's very, very important that I bring you through this process so you understand how this thing work. So you don't just, my aim is, so that at the end of the day, you don't start cramming. You just understand the process. I explain these things, in depth for you to understand. So at this stage, we'll be using this class component. So now, at the end of the day, you now understand how this class component work, how we reference them, right? And then when we now start solving DSA questions, we're not going to migrate from this class component to functions, where, because of course in your HackerRank and LeetCode questions, you literally are not going to be saying this, right? But then behind the hood, these things are going to be there, to make you be able to create your nodes and all that. So, but nonetheless, let's see what we can achieve going forward. So I think I've been able to explain why we need this linked list and why our methods are going to be written inside the linked list. Okay, so we have our push, and then with the parameter value. So now the first thing we're going to do is to have an instance of this node. So we're going to say const, and I'll call this new node. I think we've already done this before, right? Is equal new node. And then we reference the parameter that we have there, which is value. So that's the first thing. Now, we're now going to look at our first scenario here when we're talking about push. So in JavaScript, when we are talking about push, the push method is used to add value to the right? So this is the right of our linked list, our nodes in our linked list. So the push method add to the last node, right? Which is on your right hand side. Take note of that, because They are two different things. Unshift and push are completely two different things. They don't push doesn't add to this to the left, and unshift doesn't add to the right. So push adds to the end of the linked list, while unshift adds to the beginning of the linked list. So right now we are dealing with push method. And if you really don't understand these things, push, unshift, pop, so I have a JavaScript course, and it's a crash course that is for beginners, because you just have to understand these things for you to be able to follow suit here. So I have a JavaScript crash course on YouTube that I will put the link. I advise that you go through it. Just it's not long. Just go through it so you understand how these things work. You know. So we want to be able to push a node to this linked list. And for us to do that, we have to bring in our first scenario here, where we have an empty linked list. So if you look at this now, this is an empty linked list. This is not an empty linked list because, of course, we have nodes. We have nodes with a length of 4. We have 4 nodes here. So this is an empty linked list. So situation like this where we want to push a node to an empty linked list, how are we going to factor that in? So what happens here? Remember that if you look at this now, the head is pointing to the first node, while the tail is pointing to the last node. I think we've handled this in when we're talking about the structure. So in a situation like this, we're going to have the head. So let's pull this now. Okay, so now a situation whereby we have just one node, and maybe I will turn this upside down. Let me turn this upside down. Okay, so we now have this. So situation whereby we have an empty linked list. I want to push a node into the empty linked list. What's going to happen? What will happen is that the head will point to that same singular node that we're pushing, and the tail will point to that node, and then that node now will not point to this, to null. So in situation like this, it means that we have just one node. So we're going to factor this in our code. So we're going to say if we don't have head, so if this dot head, right? If there's no existing head, so how do we do that in programming? So if not this dot head, so we use exclamation mark to represent not in programming. So this is when this dot head is existing, this dot head. But if we're now looking at by this dot head is empty, it means that there's no this dot head. Sorry. So we'll put if not this dot head, right? So when we don't have this dot head, it means that the link is empty, because a situation where this dot head is pointing, or where the head is pointing to null, what that just means is that there's no node inside the linked list, right? So when we have if not this dot head, then what do we want to achieve? As I already explained, so this dot head should be equal to, remember, we've created an instance of this node by giving it this name in the variable, say new node. So we'll now say this dot head should be equal to this new node we just created, right? We created a new node. This dot head should point to the new node. And then next, this dot tail should also point to the new node, just as I've visually explained here. This dot head tail should point to the new node. So good. So we've addressed a situation where we'll have empty linked lists. Once this happens, head should point to the new node, tail should point to the new node. Now, we now want to factor in the scenario, the situation where we have existing nodes, as seen here. Now, this is how it is. So let me just remove this, because, of course, we already know that the last node is pointing to null by default. So in a situation like this, let's bring another node. So this is a new node. I'll call this node 9. I'll call this node 9. Now, we want to push this node into this linked list. I want to push this node into this linked list. And I'll bring this up. Perfect. So it's been like this before. Good. Now I want to push 9 into this existing linked list. How do we do that? So we'll now say else. Remember what we said, if there's no head, this should happen, right? So this condition, we first of all check, to check this condition, this if statement, we check this condition. Do we have a head? Okay, if we don't have a head, whatever we're pushing in should point to head. So this is what we want to push in this case. So 9 should just point to head, this should point to head. If not means there's head existing. So it's found head, right? If there is head, what are we going to do? We'll now say this dot tail. So if you look at it now, this already tail, and of course we are referencing this tail with this keyword, right? So when I say this dot tail dot nest, this is tail, this is tail dot nest, right? Tail dot nest. This is a node. This is a particular node now. So if I want to reference this node, I'll say, if I want to reference the next node, I'll say node.nest. So 7.nest is actually 5, right? So this is tail.nest. So this is actually why we're using this arrow. This arrow points to, whenever we use the word nest, we're just referencing to where this arrow is pointing to. So we're not saying tail.nest should point to the new node we are creating. And what is the new node? 9. So in this case, now this now happens. So where we have head existing, where we have nodes existing, then tail.next will point to the new node. That's it. So let's put it in our code. In this situation, we'll now say this dot tail dot head. This dot tail dot tail dot nest. I'm sorry. This dot tail dot nest is equal the new node. I hope it's well understood. Now, but that is not all. If you look at it now, we've gotten a new node here. This now push our new node into the linked list. But look at our code, look at our linked list. Something is missing here. If you can see now that now we now have to change the tail to point, change tail pointer now should point to the last node in the linked list, because tail always points to the last node in the linked list. And because we've pushed a new node into this linked list, what that means is that 5 is no longer the last node, but 9, which is our new node, has now become the last node. And how do we do that? We just say tail is equal new node. Tail is equal new node. So we'll just say this dot tail, right, is equal new node. Now, because we are adding, what do we do to length? We increment length. If we are removing, if we are minusing, we decrement length. That's all. So your length is either incrementing or decrementing, right? So it's in situation like this now, where we are adding, where we are creating node, length should be plus plus. So we'll say this dot length plus plus. So that's it. So written our push. So here I will say my linked list. Let me say, okay, my linked list. So I'll remove this new linked list. So what we're not doing is that we're not going to use our push method here. So this is, remember that this, nothing is going to be here now because we've created our linked list class component here, right? And everything was set to null and 0. So this is actually where we are instantiating this class component, right? So we are creating a new instance of the class component. So from henceforth now, we'll no longer be calling this class component, but this new instance of it that we've created here, right? So we'll now say this. Let me copy this. We'll say my linked list dot push. So we put what did we push? 9. So we'll put 9. So we'll be able to, when we run our code now, we'll see 9 in our linked list. So you see what has just happened here. You see that here. So the first, what we have here now is situation whereby we have only one node, or sorry, where we have an empty linked list. That's the first situation here. Because if you check here now, we were able to push just one node into an empty linked list, and the length automatically incremented by 1. So if you look at it now, let's point this down. You see that our head is pointing to 9. Tail is also pointing to 9. That was the first situation we had. So in order to have more nodes in our linked list, so what we'll do here is to just add more push. That's the first step. We add more push. So let's just say we have here 2 and we have here 4. Now we're pushing this now. We're pushing this 2, 4, 9 to our linked list. So let's see how many nodes. Oh, I ran one. I'm not yet. So we're pushing this 3 now. So let's see. Now that we have 3, our length is going to be 3. So you can see length is 3. Now if you look at this now, you see that the value, head value is pointing to 2, while tail value is pointing to 9. So our code is running perfectly fine, right? Now, I want us to be able to make a push, not actually repeating this push. So let's actually create an array. Let's see if we can situation where we have. So let's comment this. So I want to be able to push for this single node, pushing for single node. Yeah. So I want to, let's comment and say for multiple nodes. So this would be, what should I call it now? Let me just call it push array. So I'll say push array equal array value. Okay. So with this, we should be able to push multiple values into, so instead of push now, we'll now call this push array. So we'll say push array, and we'll now have an array of numbers here, exactly. So we're going to have 2, 4, 7, 5, and 9. So let's clear this, and we run. Okay, something is not right with the code. Oh, man. I'm sorry. Ah, so this should be curly braces. Let me remove this. Ah, what was I thinking? God. Okay, so because yeah, so let's run and see our code again. Perfect. Now you could see that we have 5. The length is 5, and when you can 1, 2, 3, 4, 5, our head is pointing to 2, and the tail is pointing to 9. So the code is running perfectly fine. So if you want to push one, just single node, we could just use dot push. But if we want to push multiple going forward, so I've created this now. If we want to use a multiple array, we want to put multiple nodes inside the linked list, so we will use this method. So I think that is okay. So the head is pointing to 2, and then we have the nest, which is also, which is now pointing to 4, right? And then we have the nest. The nest, yeah, is now pointing to 7. And then we have nest again. The nest value is pointing to 5. And now it's also telling you that there's a node. So we have our nest again. The nest value is pointing to 9. And then the nest is not telling you that there's a node, but instead it's telling you that the nest is null, as we've seen here. So this is actually how our push method works. So our push method is working perfectly fine. So that's it for the push method. Thank you very much for staying this far with me. Bye. So we'll be looking at pop, and we'll just finish push, and we learned that push is actually to be able to create a new node at the end of the linked list. Just we had this 9 here, and we're able to push this 9, this node, into the linked list. Initially it was 5. So with the help of push, we're able to push this 9. Now what pop does is that pop also remove the very last node, right? So remember, we're not talking about this, the first node, the beginning of the linked list. Here we're talking about the last. So push and pop does that. Push will push a new node into the linked list, to the end of the linked list, while pop removes the node, the very last node from the linked list. Okay, so that is what we'll be doing right now. So let's go to push, because of course, before we could pop, we must first of all add a node, right? So let's copy and paste what we have here. Perfect. So here now, we're going to put our pop. Okay, so here we're going to put our pop. So we'll say pop. So if you take note, you see that we're not putting any parameter here. And the reason for that is because we are not actually creating or passing any node to our linked list. So we are working with existing linked list. You see, push, we added this value. Why? Because a new node is going to be added to the linked list, right? But here we are not putting anything because we are literally not doing anything new to the existing nodes that is here. So we're not adding any node to the existing node, hence here is left empty. So I'm just assuming that you don't have any knowledge of these things. So that's why I'm taking this step, giving you this all the information, that all the questions that you might be asking in your head for beginners, right? For those who are already advanced, they already know why these things are like this. But I'm also making this video for beginners too, right? Okay, so the first we'll be looking at, first step here is where we'll consider if there is no head, right? So now we want to pop a node from our linked list. But what are we going to remove from nothing? So nothing is actually going to be removed. So if we don't have a node, it means that we will return null because nothing is existing. You can't remove something from nothing. So that is our first scenario, our first step here, or the first thing we'll be handling rather. So we'll say if not this dot head, so if not this dot head, then what do we want? Just return null or undefined because there's nothing, right? Good. Now that we've been able to handle that situation, we now want to handle where we now have node existing, right? Want to be able to say, okay, if we have only one node existing, so I want to put this in comment, handle list with one node. Good. So at first we've handled where there's no node. If there's no node at all inside the linked list, return null, please. There's nothing for us to do here. Now, if we now have only one node, you already know what to do, right? Now we have one node. It means that this is the head and this also is the tail. So what do we do at this state? Just copy it, remove it, right? And if that removes it, it now means that this will now head will now point to null and tail also will point to null. So both of them are going to be pointing to null. That's just it. So let me return this one as it were because we'll be using it too. So if we have only one node, head will point to null at the end of the day, because we are removing. So if we have only one node, just remove that one single node that we have. And if that happens, it now means that head will now be pointing to null and tail will be pointing to null. So we'll say if now how do we actually know if node is existing in our linked list, right? The best way we could know is by the length. If we have a node existing, then we should have at least length should at least be 1. So once length is equal 1, then it means that we have single node. Then if length is more than 1, then we have more than one node, right? So we're not going to say, we're dealing with a situation where we have just one node. So we'll now say if this dot length is equal 1, that is the condition that tells us that the node existing inside this linked list is 1, right? So if this happens, what do we want to do? I've already shown it visually. So we'll say this dot head should equal null, right? This dot head should equal null. Why? This dot tail should also equal null. Perfect. Now, if it's not equal 1, it means that it is more than 1 because that is where else now comes in here. So if this dot length is equal 1, do this. But if it's not equal 1, now there are two conditions here. If it's not equal 1, it means that it is either equal 0 or more than 1. But now if it's equal 0, we've handled that case here. So that will, if it's equal 0, we won't even have this line of code even running at all, right? If it's equal 0, it is just taken care of because saying this dot length is equal 0 is same as saying not this dot head, because if this dot length is equal 0, then it means we don't have head at all. I hope you get it. So they are the same thing, right? So we'll now say else. So the else we'll be referring to here now is when length is more than 1, right? As I said, if length is 0, this line of code handles it. So this is the same thing as saying this dot length is equal 0. Is equal 0 is the same thing because it means that there's no node inside the linked list. If length is 0, there's no node, right? So but you could see that this line is more than the other one. So let's just return what we had before. Yeah. So we'll now put an else statement here. Now we'll now look at a situation where the node we have in the linked list is more than 1, just as we've got here. And this is where we actually have the tricky parts, right? This is the area that we have to kind of traverse this list, right? Because the thing is that when we are pushing, we could just easily push a node to this place. But removing it, we can literally just say, okay, this node should go off, while tail should come this way. No, it doesn't really work that way. So we have to traverse this node. And doing that, we need to get a pointer. So going forward, we're going to create some variables. And the first I'll be creating is a pointer called current. Now, why do we need this pointer? We need a pointer that will be able to traverse this linked list, right? and keep record of all the nodes. In fact, the pointer will move until we're able to get to the particular node we want to remove. That's the work of the pointer. So it should be able to point to the node that we want to remove, right? Once the pointer is pointing at that node, then we cannot pop it. So we need a pointer that will be able to deal with that. Then we are still going to create another variable that I call the previous, in short, prev. So this prev, what it does is that, remember that if this pointer, which is current, is able to traverse this list and then get to this point, get to tail. So let me remove these two. I think we don't need them. We already know that 9 is tail, 2 is head. So this current will keep moving from node to node, keep moving, traversing from until it gets to tail, right? Until it gets to a point where you realize that, okay, this is the last node. So once we're able to figure out that this current pointer is not pointing at the last node, then we can now remove that, right? And then at the time we remove this, remember that this tail was pointing here and tail has always been here. So we need another pointer to be able to say, okay, tail, now that 9 is off, tail, go and point to so node. In that case, now we need a pointer that will keep track of every node before current. So this is node. Both of them are going to come here, right? So we need another pointer now that will point to the node before current. So as node is here, previous is going to be here. Now as node moves here, previous will move here. It should be keeping track of every node before current. As node, current move here, sorry, previous comes here. As current comes here, previous comes here. You see, this is why I said we need 2 pointers here. There are some cases where you need up to 3, 4 pointers, right? So, but in this situation, it's obvious that we just need just 2. And why do we need this first one? This current now has been able to traverse to the last node. Now we can ask, okay, since this is the last node, pop it, remove it. So we'll now have this off. Remember that tail is pointing to 9. So we should not be able to say, okay, since 9 is off, tail should now be equal to previous, which is now this pointer. So with this, we are now able to successfully pop this 9, this node, off from our linked list. So that's exactly what we'll be doing. And then we'll create the variable here because we are going to use them outside this if block. We are still going to use them inside the if block, but then we can't create them inside the if block because, of course, you already know what will happen. If we create them inside the if block, then it should happen, everything should happen within this block. So we're going to create them here. So we'll say let current equal this dot head, right? So current should, let me return this 9 where it was. So current should, yes, come here. And then we'll now say let previous, which is prev, equal current, right? Let previous equal current. So we can just leave this at the moment, right? So this is the tail, but I want to remove this for now. Let me just remove this for now. Okay, now we've handled situation where we don't have a node in the linked list. And now we also handled a situation where we have only one node in the linked list. Now we want to handle a situation where we have more than one node in the linked list. So we're going to use while loop. So we're going to say why current.next is not null, right? Because we've already handled a situation where head is 1. And now we said let current equal head. Now what we're not saying is why current.next is not null, because of course this is, let's assume now we have this situation where this is current and current.next here is null. It means that this is the last node. So we're not saying, okay, why current.next is not null? What that simply means is that the current.next has a node, right? So we're going to say while current.next is not equal to null. Good. So now what do we want to achieve? Once current.next is not null, what we want to do, just as I explained earlier, previous should be equal to current. That's the first thing. Previous moves to become equal to current. Previous should be equal current, right? Now the next step is that current should become current.next. Current moves to the next node. So current will now move to the next node. Current.next. So these two lines of code we keep running until current moves, current.next becomes null. So let's look at it now. Now current has come to the next node, which is 4. Previous is here. Now it will check again. Current.next is not null. Yeah, current.next is not null. We still have a node here. So in that case, previous move to become equal to current. and current move to the next node. So this moves now from current that it was to current.next, which is 7 now. Then it checks again. Do we still have, is current.next equal to null? No. Why current.next is not equal to null? Okay, previous, move to become current. Current, move to become current.next. Then it check again. We still have another node. Then in that situation, previous, move again, it moves. And then current, move to the next node. Then it now checks again. At this state now, current.next is null. So it says why current.next is not null, but we're already having current.next null. So this code is it, because we're not having current.next is null. This condition was not met, and the code is it. So as this happens, as this code is it means that we are done looping through this linked list, right? Because current has been able to point us to the last node, right? Now, what do we now do next? We'll now say, okay, since we're done traversing the linked list, we'll now and we've been able to point to the particular node we want to remove, want to pop. We'll now say, okay, previous.next should now become equal null. That is our point. We want to pop this node off, right? We want to pop it out from this linked list. And now we've been able to point to the node we want to pop out. We'll now say, okay, prev.next, which is pointing to current now, right, should become equal null. At this point, we'll no longer be having this. We'll now have this. So this goes off. We successfully removed it. But now, remember that tail was initially pointing to 9, right? So at this state, our code is still not complete. We'll still be having something like this. Head is going to be here, right? And tail is now pointing to null. So what we'll now do is now to say, okay, since it's like that, let's now turn this pointer from null to previous. That will now make this pointer to turn this way. So we'll just say, what we'll now say is this dot tail is equal previous. Sorry. Okay. And now that we succeeded sorry. Now that we succeeded in doing that, we no longer, of course, tail is now equal to previous, right? So this previous and previous is here. It means that tail is now equal to the last node, which is 5. So you can now see that we just successfully removed this node from the linked list. And now, as I said earlier, since we are decrementing, we're removing, length to be minus minus, right? So we'll now say this dot length minus minus. And what do we want to return? We want to return current dot value. That is the node that removed. Look at it. If you remember, at the point, look at how it was. Excuse me. So you can see how it was initially before I removed them. Look at it. It was like this. Current was pointing to node, right? And there's a value that current was pointing to, which is 9. Before we now say, okay, let previous.next become null. Now, what do we want to want to return that value that was removed, which is current.value, right? So I'm taking this time to explain all this so that you understand. You don't just need to cram this code. You understand the process. I'm just doing this visually so that you are seeing the process I'm going through to write this code. So it's not, I'm not just bringing this thing out of nothing, right? So if you're able to understand this movement, how this node moves and the pointer moves, you'll be able to actually write this code eventually when we start writing DSA equations, right? So we'll just say return current.value. And that's it for our pop. That's it. So I'll just put this. Perfect. So let's see. I hope we've not made mistakes somewhere, but of course, if there's an error, we'll go and trace it and correct it. So at this state now, we should now be able to pop. So let me see what we have here. We have 2, 4, 7, 5, 9. Okay. So here, I still want to return this one. So let me copy it. Still want to return this and then paste it here. Then here, I should now pop. That's all. So let's run our code and see what we have. So now we're using .pop. So what that means is that this one we remove. We'll now have left with 2, 4, 7, and 5. So our length will decrease from 5 to 4. So let's run and see. Exactly. So you see that 9 was removed because I console.log this .pop. So I want to see the value that actually pops off. So 9 was removed. You can see that our length has now reduced to 4. So if you check it now, you see that the tail is pointing to 5 and no longer 9, right? Tail is pointing to 4. So if I comment this, you're going to see that, let me see, leave this and run. Look at, so you see I commented this pop. We have 5. Our length is 5 because that's what we have here, right? And the tail was pointing to 9. But at the point I now pop it, 9 goes off, tail will start pointing to 5. So our code is running perfectly fine. So let me uncomment it and run again. So we have 9 removed, 9 popped off. So if we want to keep popping, we can just be repeating this pop. And then if we pop again, we're going to have 2 nodes popped off from here. So now 9 and 5 is moved. Length has reduced to 3. So it means that tail will now be pointing to 7. And if you check here, you see the tail pointing to 7, right? And if we pop again, we're going to have the 4th one removed. 7 has now been removed. We now have 2. So you can see how the code is working perfectly fine. So if you we pop again, now we now have only one length, only one node left in the linked list. It has successfully removed 4, leaving us with 1. At this point, if you check now, let me pull this off. So if you check this now, you see that both head and tail are pointing to 2 because that is what is left, right? We have 2 left. So the head will be pointing to the 2, tail will be pointing to the 2. So let's pop again. And now we're having one node left. So let's pop again and see what happens. When we now have, now length is now 0. Have you seen it? So everything has been removed. And as we stated in our code, that if we have only one node left, what should happen? Head should point to null, tail should point to null. That's exactly what we see. You can see head pointing to null, tail pointing to null, and then length decremented, and we got 0. So our code is running perfectly fine. So that's it for pop. Thank you very much. Now we want to, of course, the explanation here is that we want to shift, meaning we want to remove this node, right? Good. So when we are adding and removing from here, we talk about pop and push. So if you want to add, you use push on this side, and if you want to remove, you use pop. We just done that before. We just finished that now. Now on this side, which is the head, we want to remove, which we're going to use shift, right? Good. So the first scenario we're going to face is, of course, you already know, when tail and head are pointing to null, right? So when we have situation like that, you already know what we're going to do. We're going to say it is undefined. So when both head and tail are pointing to null, we'll say it is undefined, right? So we're going to say if this time around we can use this dot length, right? You know that this dot length, we can also use that to measure, sorry, this dot length is equal 0. It's equal 0. And what do we want? What do we want? We return undefined or no. So we'll just return undefined, right? So we are done with the first scenario. Now the second now will now be good. And this is where we now have the main issue. If you have existing node, we've already factored in if there's no node, return undefined. Now, if we now have existing node, what do we do? Very simple. Look at it. This head, this dot head should move to the next, which is this dot head dot next. That's all. That's all. That is just the movement. Once this dot head dot next moves to the next, this becomes 0 and it's no longer useful, right? So this node is no longer head. So all we now have to do is to say this. So where we have node, we say this dot head is equal this dot head dot next. Then what do we do next? Think about it. Now that we have that we decrement, that cut off that head that is no longer in use, we'll now say this dot length. This dot length. Sorry for using underscore. So that will now reduce our length. Now, once this has been removed, initially we have 4 in our length. With this decrement, with this one now that we decremented, we'll now have 3, right? But now that is the second scenario. We also have another scenario. If you look at this code very well and you look at this situation, you see that we have another situation that will be facing us. What if we now have another situation where we have only one node? That will now be, remember that we are removing from the head. Now, if we have only one node, we're going to have something like this. Good, right? And we want to remove from this side, coming from the left. Now, we now said head.next. We've written that code. Head is equal to head.next, isn't it? It means that head.next will move to null. What now happens to the tail? And at this point that head.net has moved to the null, remember that we are on shift. It means that this tray, which is this node, will be removed. And then where will the tail be pointing to? The tail has to point to null. Take note of that. So that is the last situation. So we're going to factor that into our code, right? So now we're now going to say, if again, that is after all this has happened, we now find out that length is now 0. Don't get confused. This is completely different from this. So we'll now say if this dot length, what? If this dot length is now equal 0, right? This time around, don't return undefined, because this situation is not the same with this at all. Now, this situation is before we start, we find out that there's no node at all. So we have to factor this in. If we don't factor this in, our code is going to break. If there's no node at all, your code will just break, right? We're going to have errors. So we have to factor this in error into our code. Now, but now this situation now is that we have nodes. Of course, we have nodes. That is good. Now, a situation whereby we now have only one node. That is where this situation comes in. So if we have only one node, right, this code will run because it has found a node. So head is going to be equal to this dot head dot next. So the head will move to null, right? And then we have decremented. It means that initially it was 1. We have decremented. It will now become 0. You get this dot length has become 0. So we are now saying if after running this section of the code, you now find out that this dot length has become 0, please move tail to null. Simple. I hope you're appreciating this. So we'll now say this dot tail is equal 0. Or no, sorry, it's equal null. Yeah, because tail head is already null, so tail is going to point to null. That's all. Now, if you run a code, that's going to run. But you know, this is data structure we're writing here. So it's actually very, very important that we return whatsoever that is being removed. Here, it is the head that we are removing, right? So it's better that we return it. And for us to actually return it, we have to define it, the head. So I'm going to say that, let me come here and define the head. So we're going to say const old head now, because now it has been removed, right? So it's going to be called old head. Now it has been removed. So we'll say old head is equal this dot head, right? Good. So now we have initialized it here. Now we can now return that old head. See, without this, your code is going to run. Just be clear with that. Without this, and whatsoever we're returning here, your code is going to run fine, right? That is why I did not bring it in, so I don't get you confused. This is actually what is needed for us to shift, to remove a node from the head. So it's better you return whatsoever that you're removing. And what we are removing here is this head. And I've just given it a variable. And I call that variable old head. Nothing more here. So I will now say return old head. Old head. But see, if I return this old head as it is like this, okay, let's go on so that you see for yourself. Let me not confuse you anymore. Let me not confuse you. So this is all for shift. Now we already have this. There's nothing here. Okay, I want to concatenate something. Let me concatenate something here and say so that what I've written here will bring the head. Of course, that is the reason I'm returning this, right? So it will bring the head as we did on pop. But I want to concatenate something so that it will be more clear. So I'll say, let me space, newly removed head, right? Newly removed head. Okay, and I'll close the color. And here I'll use a $sign. So for this concatenation, I'm using template literals, which is above your tab. And yeah, so I've just concatenated newly removed head to this, and then we have this. I think we're good with our code. Okay, let's run and see what we can get here. Hope there's no error. Perfect. Now see what happens here. Now this this returns an object for us. Exactly. So let me remove the concatenation so that you get it clear. I want to remove this concatenation. You see the object that is being returned so that it will be clearer. I'll clear this and then run. Perfect. So this returned an object. I'm not looking for this object, for crying out loud. I want this value that was removed. 3 has been removed. You could see it here. That 3 has been removed. The length has decreased to 3. Our code is running perfectly fine. You get it? And then if you look at it, you see the head is now pointing to 5, no longer 3. But now we now have a situation here where this code, this line of code, is shift, because I console.log it, is returning the whole object. And I'm not looking for this whole object. I'm looking for this value, 3. So all I now have to do is to say return old head dot value. Return this dot value for me. So it's going to pick just this 3 for me because that's all I want. That's the point I was trying to make. So now I can return the concatenation. And then here I'll close this and close my curly braces. Yeah. Good. So let's run our code and see newly removed head is 3. Simple, because I've used dot value. So it has just gone straight and picked the value for me, right? It's no longer returning the object for me. Meanwhile, here you see that our node, our head has moved to 5 and the tail remains where it has been, 7, right? Good. So let's repeat this again. I'm just going to repeat this line again as we did on pop. We're going to repeat this. So let me just, we don't longer need this section. Let me, yeah. Okay, so I'll clear this and run again. Now we now have 3, 5 has been removed. This line removed 3 and this second line has removed 5. We now have 8 as our head, right? And the length has reduced to 2. So if you check now, you're going to see that the value head now, the value for head is 8, while the value for 7, while the value for tail is 7, remains 7. Now let's run our code again. We want to get to a point where we have only one node, which takes care of this code. This code takes care of it. And then we also want to get to a point where we don't have a node at all, which this code takes care of it. This line of code takes care of it. So we'll run our code again and see now that we now have 3, 5, and 8 has been removed. Length is now 1 exactly. So we're now going to check if this line of code is working as expected. This line of code is working as expected because now we have length to be 1. And remember, we are working on shift, which is remove the head. If this length is now removed, we're going to have 0. We're going to have null. What happens afterward, right? So now you can now see that the head is pointing to 7, the tail is pointing to 7. Perfect. So we will repeat this and clear. We'll clear. And then run our code. Now you can now see that our code is running perfectly fine. What we just said here is that if this happens, after running this, after removing that head, and we find out that length is equal to 0, just return null for us. And it has done that perfectly fine for us. You see, head is null, length is 0, tail is null, right? Now, we now have a situation where head and tail are null. What's going to happen? Return undefined for us. Let's check that again. Let's clear this. And then we have undefined. It has returned undefined. You see that? Now it removed 3. It removed 5, which is this. It removed 8, this. It removed 7, you know? And now we now have null. And because it has found that head and tail are null, it returned undefined for us. That was why I concatenated newly remove head, so that we don't get confused. You see now it is returning undefined. Why? Because we clearly stated it here. If head and tail are null, that is, if this dot length is equal 0, return undefined. It has just done that. So if you have followed me this far, bravo, you've done a great job. Thank you very much. Bye. So we'll be looking at Unshift. And quickly we'll just go to shift and copy what we had. Bring it here. So we'll remove all of these. And we are adding, so say newly added. Then here we are just going to remove this. We'll say this is on shift. And then let's remove this. Okay, so the first thing we'll be looking at is now for the fact that we're creating a node, because we're trying to add a node to the existing linked list. So we'll have to put a parameter here and then get an instance of the node class object. So we'll call this new node equal new node. Okay. So now I want us to look at what happens if we don't have a node in the linked list, right? So when both head and tail are pointing to null, when both head and tail pointing to null, what are we going to do? If both are pointing to null, we will just add this to the list, right? So because the linked list is already 0. So if this happens, then head should point to this node and tail should also point to the node. So you already know how that works. So let's quickly put that in our code. So we're going to say if this dot length is equal 0, what do we want to do? This dot head should point to the new node. Remember, this is the new node we are creating. So the head should point to the new node, while the tail should also point to the new node. So it's that simple. While this dot tail should also point to the new node. Good. Now, but situation where both of them are not pointing to null, it means that we do not have an empty linked list, right? So in such situation, so we can now say else. In such situation, it means that we have existing nodes in the linked list, right? So now this is our linked list with existing nodes. Now, how do we now add this this node to this linked list? All we need to do is to move the node. We'll say, remember, this is a new node. New node dot next, which is this. New node dot next should point to the existing head. That's just it. New node dot next should be equal to existing head. So we say if this happens, so we just say new node dot next should be equal to this dot head. Now, but that is not all. If you look at it now, you see that something is missing here. What is it? Head is still pointing to now the second node in the linked list, because now we've added 21, we've pushed 21 into the linked list. But head, it means that head now needs to move from this node to this new node. So we'll just say head should be equal to new node. That's it. So we'll say this dot head equal new node, and this is how you unshift a node into an existing linked list. So this is when the linked list is 0, right? This is when we have one or more than one nodes in the linked list. So at the end of the day, because we are creating and we are adding, what should happen to length? We should increment length. So this dot length plus plus. And what do we actually want to return at the end of the day? We want to return this node that we just added. So I will say return new node. Return new node dot value. I want to get this value that was added, right? So that will be all. So if I come here now, I'll change this on shift, and then we added no. So I'll just add 21. We are adding 21 to the linked list. So I'll add 21 and run. Okay, we have unexpected identifier in my linked list. Oh, I see. So what happened here is that while I was deleting the shift, I removed one of the curly braces. So yeah, okay. So our code should run well now. So let me remove this and good. So newly added, you can see it's 21. And then the length of our linked list has increased from 4 to 25. We initially had 4, now it's 5. Sorry, not 25. So it has increased to 5. And if you look at it now, you see that our new head is now taking 21. And tail value is, what did I have here? Oh, 7. Okay, so it's not actually what I have here. So I have 3. Okay, it's something else that I have here. different from what is here. But nonetheless, so if you look at what is here, so we have 3, 5, 8, 7. So the tail is taking the 7 that is here, right? So that's good. And let's see where we'll have 0 in the linked list. So let's make our linked list 0 and see what happened. Now we're adding 21. So let's perfect. So you can see that our added is still 21. If you check now, the length is 1, and then head is pointing to 21, tail is pointing to 21. So our code is running perfectly fine. Okay, thank you. So that will be all for Unshift. Bye. So we want to look at get method. So quickly go to shift and copy what we have there and then bring it here. So let's remove this as usual. And I don't want to concatenate anything, so I want to remove this. Good. So I'll call this get. And let's work with the number we have here. So I have 21. The next is 2. Next is 4, 7, and 5. Good. Now, usually, so let's remove this before I start explaining. Let me bring this down. And then I'll change this to gets. So what does the get method do? So what we want to achieve here, our aim is to be able to get a particular node that the index will be given to you. So let's assume that we're given an index of 3. We're given an index of 3, and we're being asked to fetch to get the node, right, with this index. So that is just our target. And from here, you can see the index. So that's why I just pointed this index pointing. So index is 0 based, which is 0, 1, 2, 3, and 4. So at the index of 3, what node do we have? This is the node that is index of 3. Index of 2, we have this. So that's just it. So we want to get that particular node and the value that is on the index that's given to us. So of course the index must certainly be given to you, right? So once the index is given to you, you now fetch or get the node. So that's actually what we want to get here. And now when you look at this, so let me remove this index. Yeah. So of course index of 0, 1, 2, 3, and 4. Now when you look at this, the first thing we'll be looking at here is that if for any reason we go outside this linked list, we should return null or undefined. What do you mean by going outside the linked list? Now, this list starts with an index of 0. So we don't want to go anything below less than 0. So let's put that. So if we'll say if index is less than 0. Good. So we've pointed this. We don't want to go anything below less than 0. -1, anything. -2. No, we're not going there. It's already outside this linked list. So if for any reason we have this, then return null for us. Now, on the right hand side, we don't want to go, two things are happening here. We don't want to go anything above this length. Of course, we already have length here, which is 5, right? So we don't want to go above this length. Then we don't still want to go on equal to length. So we shouldn't go to greater than or equal to length. How is it? If you look at it now, you see that length, when length is 1, our index is 0. Then when we have length 2, that is, we have just 2 nodes, 1, 2, our index is 1. When we have 3 nodes, when length is 3, index is 2. When length is 4, we have length 4, index is 3. And here now we have length 5, right? 1, 2, 3, 4, 5. So we have length 5, index is 4. It means that index is equal to length minus 1. What does that actually mean? What we're trying to say here now is that if we say equal to length, if we want to factor in equal to length is 5. So index, remember that we're looking at index has been given to us, and we want to be able to get the node that index has been given to us. So if you look at it, the highest index we have here on this length of 5 is 4. So index of 5 is out of this list. Index of 5, which is equal to the length of 5 now, is completely out of this list because we don't have a node we don't have the 6th node, remember. So we want to be able to factor in on the right hand side. We don't want equal to or greater than length, right? So we'll say or index when index is equal to or greater than this dot length. Perfect. Now if this happens, what do we do? Return undefined. or you can return null, whichever your choice. Okay. So now we're not going to look at what happens when we are within the linked list, right? And going forward, I want to bring in a pointer. I'm going to create a variable called current. I want to bring in a pointer. Sorry, this should be let current equal to. I'm bringing in a pointer to actually traverse this list. Of course, we've always been doing that. So let me remove this head. I'll explain what this pointer will be doing. And then I'm also going to, so I'll say let current, let me pull this down. So let current equal this dot head. This dot head. Now I'll now bring in a counter. This one is a counter. So it's not a pointer, it's not moving. So I'll put this on 0. So this is a counter. Now let me explain what these two will be doing. These are what we'll be using on this our get method. So this current is a pointer. I want it to traverse this list, this our linked list, and point to every node. You know, it will be moving one step at a time, pointing to each node. So this will be pointing to node. Now what I want is this counter now is that, remember that an index has been given to us. So we want to be able to get to the index that has been given to us. In this case now, 3 has been given to us. Now this pointer is not actually pointing directly on the index. Rather, it's pointing on the node. You get. So I'm not bringing a counter to say, okay, when this pointer that I've called current now points on the node, right, count for me the index that was given, that is assigned to that node, that the pointer is just pointing. Now it's pointing on this node. The index is 0, of course, so it will always be initialized to 0 because the current is set to the head, counter set to 0. So both of them will start from the head. So counter is going to be at 0. Now the point now when this counter moves to .next, right? This counter, at the point I move to .next, that's the second node now, counter takes record of that movement, counter increments. You get it? Now you can see that both of them are always the same. As pointer move to the next, counter also increments. Counter move again to the next node, right? Pointer, sorry, not counter. Pointer move to the next node, which is current. Counter increments to 3. So our aim is we'll not be able to say, okay, at the time, whenever we're able to get, whenever counter is equal to the index that has been given to us, then we can now get the node that current is on, which is now 7. So this is the work of these two that I'm bringing in. So let's just put the code. It's very simple one. So now we're going to use our while loop to say why counter is not equal to index. Why counter is not equal to index? Because once counter is equal to index, then give us the node, right? So why counter is not equal to index? We want this current to make a move. You get it? So why counter is not equal to index? Current should be equal to, you already know, current.next. Just move to the next node, right? And as this happened, just as I showed, what should counter do? Counter should increment. Counter plus plus. That's all. We're just done. So with this now, once current move to next, move to this one, counter increments to 1, right? It moves again to 2, that is to the node of 4, right? Counter increment to 2. It moves again to current.next, counter increment to 3. Now take a look at this now. We said for this condition to run, counter must not be equal to the index that has been given. Remember, this index must be given to you. But at this point now, counter has become equal to the index that has been given to us. So this code is it. We're done here. And once we are done, what do we want to return? We return the value. So at this point, we just return current.value. That's this now, the value that the current is pointing to. And that's it for get method. So let's try this now. So we already have 21, 2, 4, 7, and 5. So let's put 3, as we've seen here. So the index of 3. And let's run our code and see. Something is not right. Saying index is not defined. So let's check. Index is not defined. Very sorry. So what is happening here is that we did not put index or parameter here. So that's the issue. Okay. So very sorry for that omission. Okay, so let's hit now. We have another error. Counter is not defined. Oh, so man. Very sorry. We did not define counter. So I just put just counter like that, which is wrong. So I'll say let counter equal 0. So at this stage now, I hope nothing is wrong again. But let's run. If anything happens, we'll check it. Okay, now the code is running well. So you see that 7 was given, right? 7 has been picked because that is the index that, yeah, the index is 3, and the value on that sitting on that index is 7. So our code is running perfectly fine. So if we put index of 0, we should be expecting 21, right? So let's clear this and run. 21, perfectly fine. And when we put index of 4, when we put index of 4, we should be expecting 5. Perfect, 5. Now let's now put index of 5. Remember that our length is 5, so let's put index of 5. We should be expecting undefined. Perfectly undefined. Have you seen it? Why we're having this is because I'm returning the linked list. I'm returning this linked list. See, our console.log linked list. So that's why we're having this. So let's clear this now. We're going to see undefined. Look at it. Now, if we now put -1, we should still have undefined because that's what we stated. It should not, the index should not be less than 0. So let's clear this and run. We're having undefined. Now, if we put 6, which is greater than the length, now we've already tested for equal to length. Our length is 5, so we've tested for 5. Now let's put index that is greater than length, so which is 6 and above. We should still have undefined. Perfect. Our code is running perfectly fine. So that's it for get. Thank you very much. Bye. So we'll be looking at set. So on a quick one, let's go to our get method, copy everything and bring to set. Set is going to be the quickest and the simplest. Just put a line of code or thereabouts. So we'll change this to set and change what we have here to set. Now, this is kind of a continuation of what we've done on get. So we're not going to remove any thing from here. This line of code will remain because what happens in set is, now that you've gotten this value with the index of 3, this is the index that was given to us. Now you've gotten the value, set another value to it, right? Change the value, change this existing value and put something else. So for set, 2 values will be given to you. First is index, and then the second is the value they want you to add. So let's say 17 or let's say 16, whichever. Okay, so these 2 will be given to you. This first one is the index you are targeting. So you first of all get this index, get the value with index of 3, and then set this number, right, to it. So at the end of the day, when you are now done, 7 will no longer be the value, but now 16, right? So that is what we'll be doing. So for the fact that we have to first of all get the node that with index of 3, it means that everything we've done remains as it is. Now that current is now pointing to this value, what do we now do? All we just have to do is to say, okay, since we've gotten to the node we're looking for, right? So current dot value should just become equal this new value, right? So here we worked with only index, but now a new value has been given to us. So we're going to have 2 parameters here, value, right? So a new value has been given to us, which we'll be working with, right? So we want to change the current value to this value. So it's just a line of code. We'll just say at the end of the day, since current is now pointing to the value we want to get. Now we've gotten it is 7. So change this value. Change this current value should become equal to the new value that was given to us. Current value is equal value. That's all. That's all. We are done. So we return current value. The fact is that you can literally return anything. Normally in DSA question, they will tell you what to return. So whatever they ask you to return, what you'll be returning. Sometimes they'll tell you to return the full head, right? So in that case, you just return the head. Sometimes they ask you to return the value that you just changed. So and now once you just change that value, this current value becomes the new value, right? So in this case, now we're returning the value that we've changed to, which is because of course current value now has become equal to this value. So which literally has made current value equal to this value. So that's what we'll be returning. So here now we'll change this to set. So let's see, we have 21, 2, 4, 7, and 5. So like I said, they'll give you 2 values there. The first is index, the second is the value they want you to change to. So here we have 16. Now let's run our code and see what happens. I want to believe that everything is fine. Okay, but if not, of course, it will throw an error and we will deal with it. So let's run our code and see. Perfect. Everything is working perfectly fine. So we just, this line of code is what you add from get to set, right? Current value becomes equal value. So if you look at the value that we just set to 16, because I console.logged it, right? So let's now check if our code worked well. At the end of the day now, we will no longer see 7, but we'll be seeing 16 in place of 7 because it has now set this node to 16. The value of this node is no longer 7, but 16. right? So let's check it. So we have our head 21. Good. Now let's step by step. We'll go to the next node. The next node is 2. Fine. We'll go to the next node. The next node, the value is 4. Very perfect. Now let's now check the next node. The next node is now 16 and no longer 7. So our code is working perfectly fine. You get it? It has now set this node to 16 and not 7 anymore, right? So when you check the node next now, which will now be the tail, you see that the next value is 5 and the next is null because we got into tail. So our code is running perfectly fine. So let's now check. Let's just put it on 0 and see. So that is it for set. So let me clear this. We'll check this now. Now you're going to see that the head will no longer be pointing to 21 but 16. Look at it. Head is pointing to 16. So we don't have 21 again in this linked list, right? So that is it for set. Thank you for following me this far. Bye. So today we'll be looking at insert, and we'll quickly go to set and copy from set, and then bring it up here. So let's see. We're going to remove this. So I will leave this line of code. Then I will make this insert and change this to insert. Good. So now let's look at what we have here visually. So we have 21, 2, 4, 7, and 5. And we're giving this index and value. Normally on insert on set, what would have just done is to enter this 13 on this index of 3. So what would have done here is to change this 7 to 13. That is for set, right? But for insert is completely different. So what they're asking us to do is to insert this value on index of 3. What that means is that the former index of 3 will still be existing, but it will now shift. While we now have this node 13 pointing like this. So we're going to have something like this. That's different between insert and set. Set will just change the value of the node on the given index, right? But insert will go and insert the new value that's on given index, right? So, and this is the new value that's been given to us 13. Now we're going to insert it on the given index, which is now index of 3. So at the end of the day, here will now become index of 3. It will auto, it will increment itself, right? So here will now become 4, while here become 5. So at the end of the day, we're going to have 5, index of 5 with length of 6, right? Because here we have length of 5. So once we now insert another node, our length will now increment to 6. So that's the difference between set and insert. So our first step, our first line of action here is to make sure that we are not out of bounds, right? Now remember that we are not on set but on insert. So on insert, we're going to say if index is less than 0, which is, we factor this in, we go below 0, right? So anything below 0 is undefined. Undefined, yeah. So, but we've been using null and undefined. So let's look for something that will return, maybe a string. So we'll say, what can we put? We'll put out of bounds. Yeah. Because that is even what happened when, yeah, we're out of bounds. So once we go out of this linked list, we're literally out of bounds. So that does it. So we'll just put a string. Remember, we can return whatever we want to return, right? So we're saying that once you are out of this linked list, return out of bounds. Now, once index is less than 0, we already used to this. Or index is greater than or equal to, but we want to remove this equal to. Now that is, I will now explain. What we'll now have is index is less than 0 or index is greater than length. We're going to factor another scenario where index is equal to this dot length. When index is equal to this dot length, something else is going to happen. For insert, it's not out of bounds. That's the fact. Now let me explain that. Now if you look at this, we agree that on set, if index is equal to length, then it is out of bound because we are trying to set. Remember, for set, we are not adding new node, we are not creating a new node. So we are trying to set a node on index that is not existing. So if index is equal to length, it means that we're having index of 5. And here, index of 5 here is not existing, is null, right? So we can't set a node that is not existing. Now, but for insert, we are not just working with available node. We are actually adding a new node. So if index is equal to length, let me make this now. So this is 5 now. The length we have here is 5, right? And of course, we know that index is equal to length minus 1. So which has given us, when we have length of 5, we have index of 4 because index is 0 based here, right? So we now say, okay, insert 13 on index of 5. Here, at this state now, index is equal to length. This is the length. So what we're now saying is insert 13 on this position where index is not, where we have this node, right? When we have this node dot next, so we'll go and insert this node here, right? So if there's a pointer pointing this node, right? Let's assume that we'll bring in a current to come and point at this node. This is the last node where we have, and our length is 5, right? So what we're going to do now is, at this point, current, we should just move current.next, which is this, because we are putting in a new node, we are inserting a new node. So we can actually factor in when index is equal to length. And at that state, what happens is that push operation happens, right? So at this case now, so just take note of that. For insert, index being equal to length is not out of bound. Take note of that. But for set, index equal to length is out of bound. Thank you, which I've explained. So we're going to say if index is less than 0 or index is greater than this dot length, then return out of bound. So let me remove this current because we're not ready to use it now. Okay, so that is the first step. So at this state, we're going to create a new node, having handled this situation, right? So now I want to start working on our node, right? Okay, so the first thing is we're going to create our new node as we've always been doing. New node is equal new node, should be value. Good. Now, having done this, so we want to take different, let's take it step by step. The first step is when index is equal to 0, then we have to carry out Unshift operation, right? So when index is equal to 0, at this time, it means that the new node will come this way, right? So if index is equal to 0, what is going to happen? What will happen is that the new node will point to this dot head, will point to the head, right? So new node dot next will point to head, because of course you know that when we talk about the new node, this is just the new node. Why new node and next, this arrow, right? Okay, so let's do that. So at this state, we'll say if index is equal to 0, what do we want to happen? Just as I explained, so we'll say new node dot next should be equal to this dot head. So this will now come this way. Good. So this new node dot next will point to head, right? But if you look at it, you find that this is still not perfect, right? We still have something to do here. Our head is still pointing to the former head. So as usual, our head pointer will now point to the new node. So head will become equal to new node. So we say this dot head will become equal to new node, right? Good. Now, we still have to factor something here. We still have to factor something in at this point. So we'll now say, assuming that we have null, assuming that before now, head and tail, let me duplicate this. Assuming that before now, head and tail, head was pointing to null, and tail also pointing to null, right? And then this operation is going to happen because at this point, we can literally just factor in. So okay, index could be given to 0 here because there's nothing in the list. The list is still empty, right? So this code is going to run. What now happens? This first line of code is going to run. When it runs, we'll now say new node.next points to head. So it's equal to head, right? It's now pointing to where head is. Head, remember that head now is pointing to null. This is when we have empty linked list, right? Now, at this point now, we now said, the next line now said, head should point to new node. So head is now pointing to new node. What now happens to tail? So we have to factor this in. So we'll now say, if this dot tail is equal to null, what do we want? We want this dot tail to point to new node. We want this dot tail to become equal to what? To become equal to new node. Perfect. So now let me explain what has just happened here. At the point where index is 0, right? Insert this new node. That is what we've done here. This is when we have nodes existing in our linked list. So at this point, everything is fine, right? We have nodes existing in our linked list. So make new node.next to point to head. This has happened. And then move head to new node. So now at this point, we have a perfect system, right? Automatically, this will become index of 0, 1, and all that, right? So we've got a perfect system here. But now, we now have another system where we have empty linked list. And that empty linked list literally means that head is pointing to null, tail is pointing to null. It still factors in where index is 0, right? So at this point now, new node will point to this. We point to the head. Now the second line of code, head, will now point to the new node. And then we are left with tail pointing to null, right? So what we're now saying is that if for any reason you are done running this code, check if tail is pointing to null. So if this condition is not met, if for any reason this condition is not met, it means that we have this system. It means that this is what we have. Everything is fine. There are nodes existing in the linked list, right? There are nodes existing in the linked list. So because if tail is not null, it means that tail was existing before. There's a node existing in the linked list which has been assigned to tail, or which tail has been assigned to, right? So, and for the fact that this condition was not met, nothing is going to happen. This whatsoever we have here is not going to take effect because the condition for this code to even run was not even met, right? But if you are done doing this and you find out that tail is pointing to null, move tail to new node. Very simple. Move tail to new node. So we now have our perfect system where head and tail will be pointing to the new node, right? And then the node.next will be pointing to null. Hope that is clear. Good. So let's now move to where we now have, I think I will write a comment here. Let me drop a comment here. Let's say insert at the head. So we are inserting at the head at this point. Now, once we are done doing this, what do we do? Because of course, length will automatically increment. So we'll now say this dot length plus plus, and we want to return what? We want to return the new node. Now that's it for when index is 0. So now we're not going to move to the next step. And the next step is we have to insert at the end. That is when I told you that index will be equal to this dot length. So insert at the end. And at this point, we'll say if index is equal to this dot length, what do we want to do? So I believe I've already explained that earlier, so if index is equal to length, what do we want to do? We want to push, right? And for us to successfully do that, you can see that we have tail. So tail.next should point to the new. Let me remove these ones now. I no longer need them. Tail.next should point to the new node like this. So let's put that in our code. So if this happens, we'll say this dot tail dot next. Good. Is equal new node. Now this has happened. So we'll now say tail is now equal new node. Let's put that again. So we'll say this dot tail is now equal new node. Now, let me drop this one. So this has taken care of when the index is equal to length. And at the end of the day, what do? Let me just copy this. We'll drop this here. Good. So for the beginners, please do not get yourself confused with this, so that you don't start asking yourself, why is it that in this section, this dot length and return was just directly after this dot tail equal new node. But here, there's a curly brace before this. So if you look at this code, you see that we have an if statement inside if statement. So this curly brace is actually for this if statement. So this is the block for this if statement. So let me cut it off. You see that everything is within this if condition, right? So, but there's an if statement inside it. Here, we don't have a nested if statement, right? That should have another curly braces. I just want you to understand so that you don't like, why is everything straightforward here, but it's not on this if index is equal 0. Okay, so having handled that, we will now have to insert at the middle, right? So let me copy this again, the comments. I'll say insert at the middle. Good. Now, for us to insert at the middle, we have to traverse this linked list, right? So I will create some variables. So I'm bringing in this current to help us to traverse this linked list. So I will remove this head. So I will say current is equal to head. But first, I'll first of all create the variable, right? So I'll say let current initialize it to say is equal to this dot head. Is that this? No, that is not this dot head. Good. Now I'll bring in counter to keep record of every step this current node, this pointer move takes, right? So we've used this before, you understand what I'm saying. So we're going to say let counter equals 0. Now, what is our aim of actually using this tool again? Because for every pointer we bring in, we should be able to define why we are bringing them in. We've been given this value to add to a node and then insert it into our linked list. This value is 13, right? And then they've told us where to insert it. We should not just insert it anywhere. Insert it at an index of 3. Perfect. So remember that this counter works with the index. Why this pointer points to the node. So every node the pointer points, the counter takes care of the index that the pointer has pointed. So now the current is pointing currently at the first node. The counter has been set to the first node, which is 0. The current makes another move to the second node. The pointer increment by 1, right? Now we want to be able to point to the node before the given node. This is our given node, 7, sitting at an index of 3. So we want to be able to point at the node before the given node, or in a better way, we want to be able to get to the index before the given index, because here index was given to us, not node, right? So we want to be able to get to index before the given index. This is given index, and the index before the given index is index minus 1. 3 minus 1 is 2, right? So we want to actually get to this node. Once we're able to get to this node, we can also, okay, this node now, current is sitting in, this is now current. We can now say current dot next should become equal to the new node. Current dot next, where's the new node? Let me just duplicate this. I can't see. Okay, this is the new node I was working with. Look at it. So let me bring it. We'll now say current dot next is now equal to the new node that has been given to us. Now everything fitting. So we've successfully now been able to insert this new node into the linked list. So that is why this pointer, this current is coming in this pointer, and then the counter takes care of the index that the current is pointing at. So that's the work of these two variables I've just created. So we'll now say while this is pointing at to the head. Good. So we'll say while counter is less than index minus 1, I will explain. While counter is less than index minus 1, what do I want to achieve? What is wrong here? Sorry for this mix up. While counter is less than index minus 1, what do I want to achieve? I want current to be equal to current.next. Now, let me explain. Let me shift this one down. So I've said while counter is less than index minus 1. Remember, this is index minus 1. This is our given index now, 3. So we'll use this now that has been given to us case study, right? 3 now is our given index. Remember, our aim is to be able to point at index minus 1, which is 2 here, right? So in that case, counter must not be equal to index minus 1. Rather, counter should be less than index minus 1. So for current to make a move, counter has to be at least below index minus 1, because our aim is for counter to be equal to index minus 1, right? And if we now factor that in and say, okay, counter should be equal to index minus 1, and if that condition is met, current should be equal to current.next. It means that even when counter is sitting at the position we want, this code is still going to run. So we now have current equal current.next. It will now move to the position where we want to shift this in, and we don't want that. Where we want to insert this node, we don't want that, right? So what we want is counter should be at least below where we are going to, at least a node below the node we want to arrive at before this code could run. Now let's handle it now visually so you understand better. Now we said while counter is less than index minus 1, current should become equal to current.next. And remember, counter has been incrementing, so here we'll put counter plus plus. So this is just what happens here. Counter is not equal to index minus 1. Counter is 0 at first. So it checks. Counter is 0. Good. It's not up to 2. It takes this move. Counter increment to 1. Counter increment to 1. Then it checks it again. Counter is less than index minus 1. Yes. So this condition is met. Current moves to the next. The next line. Counter plus plus. Counter increments to 2. It checks again. Counter less than equal to, counter less than index minus 1. No, this condition is not met. Counter is now equal to index minus 1. Index given index is 3. So index minus 1 is 3 minus 1, which is 2. At this point, this while loop, this condition is no longer met. This while loop stops running. It exits. You get the point. So now that it has exited, what do we now do? We have been able to achieve our aim. Our aim is for current to be sitting on the index before the index that was given to us. So now that we've achieved this height, what do we now do? We'll now say new node.next. Remember, this is current.next. Here is current.next. So we'll now say new node.next should be equal to current.next. So at this point, new node.next is equal to current.next. So you see that we've been able to insert this new node into the linked list. Now, so we'll now come here and say, at this point, we'll now say new node.next should be equal to current.next. Now we can now move our pointer and say, okay, current.next equal new node. So we'll now say current.next. So by doing this, if you check now, so we've been able now to say current.next equal, this should be equal new node. So by doing this, we have successfully pointed current node, right, to point at the new node. So everything is now linked successfully. You get, and once that happens, what do we do again? We increment length and return, increment length and then return the node, the new node. Good. So this is it for insert. So if you look at the steps are quite not that difficult. It's just for you to be able to actually know how this movement happens. And once you're able to follow this movement, right, you are literally going to, in fact, once you're able to follow the movement well, you'll be able to know how to write your code line by line. Okay, so now let's test what we've done and see. So here we'll say we're inserting 13 and not 16. So we'll change this to, so let's, okay, we're having an error. Unexpected identifier my linked list or something. I think we're also missing another curly brace here. So I think I mistakenly deleted it. Okay, good. Now let's run. Perfect. So our code is running well. Okay, so let's now check. We'll see that on index of 13, let me increase this. I'm very sorry, index of 3, this value was inserted. Head is 13. Something is not right with our code. Oh, perfectly fine. I didn't change the index. So yeah, everything is right. So you can see here that index is 0. Good. So this has now changed head to 13. So if we go next now, you see that next is now 21. So it did not actually change, just shifted 21 to a new index, right? 21. Next will now be 2, right? So, and so on. Next will be 4, 7, and all that. Okay, so let's change this to what we're given, which is 3. 3. Perfect. So let's run, clear and run. Now we have our length 3. Good. Head remains 21. The next now, which is index of 1, is 2. So the next will be 4. That just do. The next will be 4. And now the next will now be 13 before 7. So next will now be 13. You see, our code is now running perfectly fine before 7. And then the last, which is the tail, is 5. There's no head again, there's no node. Next is null. So the code is running perfectly fine. So let's test other scenarios. So we'll have when index is, we've tested when index is 0. So when index is equal to length, our length is 5. Remember, the given index, this is the node. Before now, we have length of 5. So if you see check, we have length of 5 here, right? So let's say 5. So let's test that and see what happens. Let's clear this, and then, so what will happen here is that this node will go to the tail. So we'll just go and check the tail straight. So let's check. We see have our list, our length of 6. We'll check the tail. It's working perfectly fine. So here now tail is 5, but now after the insert, tail is now 13. Perfect. So let's test when, what else should we be testing? At -1, -1, when we're out of bounds. So let me clear this. You can see clearly out of bounds. Remember that we're getting this because of this. I'm logging the linked list into the console. So out of bound is now returned because out of bound there's no insert, so it's returning what we had before, which is this. Good. Now let's also test for 6. 6 is above the length that we have. Our length is 5, so 6 should give us out of bounds too. Exactly. So the code is running perfectly fine. I think there's one section we've not tested. Good. Let's test this scenario when we have empty linked list. Let's test when we have empty linked list. So we should be able to point head and tail to null after head and tail to the node, new node, and then head and tail dot next should point to null. Good. So let's do this. This should be 0. Remember. So let's code. We've got our length to be 1. You can see next is null. So head is pointing to 13, tail is pointing to 13, next is null, dot next is null, tail next is null. So our code is running perfectly fine. Good. So this is it for insert. Thank you very much. Bye. So today we'll be looking at remove, and on a quick one, let's go to push and copy what we have on push and then bring to remove. Good. So here we're going to write remove and to be looking at the index because we'll be using the index to track the node that we'll be removing. Okay, so as usual, let's look at visual representation of it. So what our target is, a given index will be given to us, an index will be given to us, sorry, and then we'll track that index and remove the node that is assigned to that index. So here, index of 3 has been given to us, and we'll be able, that is the node, it means that the node we want to remove now is 5. And once we remove that, the length will decrement, and then index will have to update itself. So let's write our code. And of course, we have to first of all consider situation where we are out of bounds, right? And for for remove and set are the same thing when we talk of out of bounds. Just take note of that. Remove and set are the same thing. So let's just quickly go to set and copy what we have for the out of bounds. So say set. Yeah. So remove and set are the same thing for out of bounds. And I literally don't need to explain this again because that would mean a lot of repetition, right? So I understand you know what all of these mean. So you can go back to set and look at the video again so you understand. Okay, so haven't handled out of bounds. So let's now deal with why we are here. So I want us to create a variable. The first variable is going to be, I call it the removed node. So I'll say let's removed node. Now I'm doing this so that I could store. We're going to have our pointer remove node. So this is it, right? But I'm creating this variable here because I want us to store everything that happens here on this remove node, because at the end of the day we are going to return this remove node, right? So it's actually what we'll be returning. So I want everything that happens to be stored on this variable. So now we'll now look at our first step, and we'll consider when index is 0. So if we have index to be 0, right, as we have now, you can see the index is 0. If we have index to be 0, it means that we want to remove this head, right? So let's put that into consideration. And what are we actually going to do if we have to remove the head? All we literally need to do here is not going to be much. Just point this remove node, because this remove node will be pointing. We want this remove node to actually point to the node we want to remove at the end of the day. So if the index, if we're targeting index of 0, right? So let's say here now, we're targeting index of 0 here. We're giving index of 0. All we need to do is point this remove node to head, and then point head to head.next, because of course we need to update head now. Once this remove node point to head, it means that we want to remove this node, right? And for us to remove it, of course, we did this on shift. Once we remove this, it means that this is going to be null. So we point this, and for this to actually be null, because right now head is still pointing to this node. For us now to invalidate this node, we have to remove this head from this node. All we just need to do is to say, okay, head now point to head.next. Once this happens, this node becomes useless. This is no longer head. Okay, so let's put that in our code. So let me return this first. So we'll say if index happens to be equal to 0, right? So what do we want to do? We'll say removed node should be equal to this dot head. And having done that, now is now equal to this dot head. Then we want the head to point to head.next. Head should point to head.next. So we'll say this dot head should be equal to head.next. Head.next. Good. Now, but when you look at this, factor this scenario in, that we have only one node in the linked list. So let us assume we have this node in the linked list. Let me bring this out. Now let's assume we have this node in the linked list. Remember, this is the head, and let me turn this tail. Okay, so I've turned the tail. So and this is the tail pointing to the same node, because we have just one node in the linked list, and then this node is pointing to null. Good. And we have said, let me shift this. Any need? Okay, let me shift this. So we have said that we have created this variable now, remove node, and we said if index is equal to 0, remember we have one node, so, and we assign this node to an index of 0. So it means that this C factors in, and we say, okay, now we've gotten index to be equal to 0. Remove node should point to head. Now remove node comes here and point to head, right? And then we now said head point to next, head point to next. At this section, what now happens to tail? If we leave this like this, right? If we have more than one node in the linked list, everything is going to be fine. But at the state where we now have just one node, these 2 lines of code are not going to be enough. So now we're now going to check. Okay, we'll now carry out another check inside this if statement. And so, okay, if at the end you have done this, and you find out that tail is not equal to null, you find out that tail will now say if this dot tail is not equal to null, what do we want it to do? Move tail this dot tail to become equal to null. That's all. I believe this code is clear and readable enough, right? So once you just find out that tail is not null, so move tail to null, right? At the end of the day, this becomes our remove node. So length will decrement. We'll now have head pointing to null, tail pointing to null. We're going to have empty linked list, right? So that has been taken care of. So now I want to factor in what happened when index is not equal to 0. We've handled what happened when index is 0. So we want to now look at what happened if we're given an index of 1 or 2 or 3 or thereabout to remove, right? So here now we're going to say else. Now, at this state, you already know that we have to traverse this linked list. So we're going to need a loop. We need to loop through it, right? So we're going to need a counter. 1. I'm going to need a counter, and I'm going to need a previous node. These are the variables I'm going to create. So I need a previous node. I need this remove node. And then I've already created this remove node. And I'm creating this counter. I will explain the function of these two, right? So I'll say let previous node equal something. I'm going to put what it will be equal to. Then I'll say let counter, of course, counter always is on 0. Sorry, this should be counter equal to 0. Good. So the work of this previous node is, if you look at this issue, the challenge we're having now, you see that we need a pointer that will be able to point us to the node before the given index. The index before the given index, or the node before the node we want to remove. And that is the work of this previous node, right? So this previous node is going to traverse this linked list and then stop at the node before the node we want to remove. So that at the end of the day, we can now say this is equal to this.next, So we've done this before, right? So that's actually how, and as this one takes a move, the counter takes record of the index or the node is pointing, right? So that's actually what we'll be doing. So we'll say let me make this previous node and not previous node. Let previous node equal, what will be equal to head. So we'll say this will be equal to this dot head because it must start from head, right? So let's remove this head now at this state. So this is now starting from head. Why can't I start from 0? Why? Right? Good. Now we'll now say while counter is less than index minus 1. So this is no longer strange to us because we've handled this kind of scenarios before. So I don't really need to start over explaining again, repeating myself, right? Okay. So while counter is less than index minus 1, what do we want to do? So this has actually been handled on a SAT for those who perhaps just jumped into this section, right? This has been handled on a SAT. So maybe you could, if you are not clear why this is happening, check on the insert link list and you'll be able to get clarity on this condition, right? So why counter is less than index minus 1, what do we want to achieve? We want previous node to become equal to previous node dot next. We've done this before in SAT. Previous node become equal to previous node dot next, right? So carry this, write it and say previous node should become equal to previous node dot next. Good. And then as this moves, the counter increments. Simple. So say counter plus plus. So let's carry out the movement visually. So why this is less than index minus 1? This is the given index. So this is the index we're talking about now, right? And the given index here is, when I say index minus 1 is 2, right? So why counter remains less than 2? Let me take this because it's starting from head. Why counter is less than 2? Previous node should move to previous node dot next, right? So it checks, is this kind of condition met? Yes, counter is 0. So previous node moves from previous node to previous node dot next. So this moves to next. Then counter increments. Counter becomes 1. Then it checks again. Is counter less than 2? Index minus 1, 2. Yes, counter is still less than minus 1, index minus 1. So this moves. Remember that our target is this node, which is this index. So as it moves, counter increments. Counter increment to 2. Now this could check again. Counter is less than index minus 1, which is 2. No. Counter is not less than 2, but rather counter is equal to 2. And for the fact that this condition is not met, this while loop exits. We're done with this while loop, right? Good. Now that we are done with this while loop, because we are succeeded now in pointing, having a pointer pointing to the node before the node we want to remove. What do we now do? We now carry this node and say, okay, we now say remove node should now point to the node after the previous, which is previous.next. So we now say remove node is equal to previous node.next. So we'll do that. We'll now say remove node should be equal to previous node.next. Then, now that we've achieved this, we've not still removed this node. And for us to remove this node, what we now need to do is to move this pointer, this previous node, right? Previous node.next should now point to remove node.next, which is 9, the next node after remove node, thereby invalidating this node, right? So previous node.next, which is this pointer I'm holding, should point to remove node.next. Look at my arrow now. So this arrow, this node now is no longer pointing at 5, but now pointing at 9. Hence, this node is no longer valid. It has automatically invalidated this node, this remove node, right? So let me now put it this way. And what will happen? Length will decrement. Index will automatically also decrement. We'll now have this. So at the end of the day, this is what we're going to have. So we'll now let's put it in our code. So we'll now say previous node. What is happening? Previous node. It should come this way. So we'll say previous node dot next. Previous node dot next. Right? Remember, previous node dot next should point to remove node dot next is equal to remove node dot next. Okay. And once this happens, we've been able to successfully remove our given node that we are asked to remove. So everything is fine at this state. But now, if you look at this too, there's still one more challenge we're going to face, assuming that we were removing the last node in the linked list. So let's assume that we're giving this node 4 to remove. Node 4. So let me just pause and rearrange this thing so I don't take much of your time. So assuming we're giving index of 4 to remove, right? Look at what is going to happen. That another line of code is needed here. So previous node now will now move. Previous node will check here. Okay, remember index minus 1 is 3. So at this time now we want previous node to target 3. Right? So it means that this condition is still met. This condition is still met. Counter is not equal to index, so counter will move from previous node to previous node of next. It will now point here. Counter increments. So we'll now have 3. Just follow me. Now at this state, this while loop will exit because it is now equal. It's no longer less than index minus 1. It's now equal to index minus 1. So while loop will exit. Now this one will now come in. Remove node becomes equal to previous node dot next. Yeah. So you can already see that this is, remember that this is null. Remember, yeah. So you can already see that this is the last node and this is the node we want to remove. And then previous node now makes a move. Previous node dot next now points to remove node dot next. And you know that remove node dot next is null. So previous node dot next will point to null, thereby invalidating this node. Now, can you now see, so this remove node has finished, this pointer has finished its work. Can you now see that tail is actually pointing to nowhere right now? So previous node is now pointing to null. Tail was initially pointing to this node 9. We now have to factor in what will happen to tail. Where will tail be pointing to? Because right now tail is not pointing anywhere. It's not even pointing to null. It's not pointing to 5. It's still pointing to this 9 if we don't remove this tail. So at the end of the day, if you don't remove this tail, you see that every other section will take place, but you see your tail pointing to this 9, right? So we now have to factor what happens if we have this situation where the last node is the node that we are removing. So we're not going to say if previous node dot next, now that we have moved previous node dot next to now point to remove node dot next, which is now pointing to null. If previous node dot next is pointing to null, what do we want to do? Tail should be moved to previous node, because we still have list node in the linked list. So at this end, 5 now becomes our tail. Are you getting it? So that's just that simple. So let's go back. So let's now say, now, if at the end of this, we now find out, we now carry out an if statement, that we now find out that previous node dot next is pointing to null. It's pointing to null. Please just move tail, this dot tail to previous node. Simple. Move tail to previous node. This should be pointing to previous node. And that's it. We're done. So we will now, at this state, decrement. So we'll say this dot length minus minus. And what are we returning? Remember, we're returning this node, this removed node. So because that is the node we have just removed. So we want to return it. Return removed node. And that's it. So let's test our code and see how it is. Now here I'm going to, let me copy this, and so here I'll change this to remove. Good. And index, so we're removing index of 3. Let's put 3, so index. Okay, good. So let's test and see what we have. Perfect. So you can see that our length has decremented, has reduced. 1, 2, 3, 4, 5. We have, by default, we have, before this remove line ran, we have length of 5. So, but now you can see that at the end of the day, we're not having length of 4. Let me console this so that we could see the node that was removed. So let's run again. So we now have 5. You can see that 5 was removed, right? Good. Now let's check if it was properly done. So we have head, yes, the first head, tail is 9. That's good. So the next node will be 4, which is index of 1. The next will be 7, which is index of 2. And now we no longer have 5 because 5 has been removed. So our next node will now be 9. So let's check now. You see, our next node is now 9. And 9, the next is null because 9 is not tail. So this is perfectly running well. So let's check on what I'm checking again. If when we have index of 0, let's check what happens when we have index of 0. So 2 will be removed. 4 will become our head. That's what we should target. What did I just do? Head is not defined. Head is not defined. So I believe you are saying why we're having this error, right? So the challenge is that I entered head.next. Remember that we are referencing this class object, which is node, right? And we're using the this keyword to do that. So, but I just came here and put head.next. So this should be this.head. Forgive me for that omission. Okay, so let's check again. So now we are removing the head, right? So good. We can now see that 2 has been removed, and then we now have head pointing to 4. So we are good with this. So let's now remove index of 4. Remember that we cannot remove equal length. We'll also test that. So let's remove index of 4, which will remove this 9. So we'll say 4. Let's clear this. So at the end of the day, tail will be pointing to 5. That's what we should target. We'll have our head. Now 9 has been removed. Head is 2, tail pointing to 5. So we are good. Now at this state, let's put equal to length. We should have undefined because that's what we put here. Where's our return undefined? So our code is running fine. And of course, for the fact that this is running because we have this, you already know how it works. So you check this line, there's nothing to remove because we are out of bounds. So return the linked list that it initially had. Okay, so what should we be testing again? We should be testing -1. That should also work because everything remains as it were, undefined. So what should we be testing again? We should be testing, I think we've done every necessary test we need to do. Okay, we have a condition here. Good. So let's test this. So when we have single node in the linked list, we have to put that into consideration. So let's say we have just 1. in the linked list, and index is 0, right? So let's see what happens. Now you can see that we now have the 2 removed. Head is pointing to null, which is what we did. We explained that earlier. So the tail is also pointing to null. So our code is running perfectly fine, right? Yeah, so that is good. So I think we've also tested removing the last node, and we confirmed that the tail was pointing. Yeah, let me return this. We tested removing 4, and we confirmed that the tail, we wrote a code here that should do this. So let's look at the tail. The tail is now pointing to 5, and which is this. So our code is running perfectly fine. So this is it for remove on linked list. And you follow me this far, you've done a great job. Thank you. Bye-bye. So today we'll be looking at reverse. So quickly, let's go to push, copy what we have on push, and bring to reverse. So we just put here reverse. Fine. So let's look at what we'll be doing here. And the first thing we're going to do is that we're going to get our pointers. So we'll be using 3 pointers at this for this reverse, and I'm going to explain what each and every one of them will be doing. So we're going to get our current node. Of course, current node will be pointing to the head. This is what we'll be using to traverse the linked list, as we've always been doing. So it will, let's remove this head now. So we'll say current node should point to the head. So here now we're going to select current node equal this dot head. Good. Now we're going to get a previous node. Now, as current node is, remember that our task, our aim is to reverse this linked list. So, and for us to reverse this linked list, we have to traverse this list and then move every pointer's nest, every node nest, sorry. All the node nests are going to be turned the other way around as we traverse the linked list. So, it's a gradual process. But then, you see, at the end of the day, all the node nests we keep traversing, we keep turning the other way around, right? So, what that means is that as 2 is pointing to 4, it will eventually start pointing to null. So if 2 is going to be pointing to null, we need to keep a track of where this 2.nest, this node.nest will point to. That is previous node. So this will take track of that. Let me bring this out. So now this 2 now, this node.nest need to point to null, right? It needs to point somewhere. So we should be able to keep track of where this node is pointing to. So, and this pointer will help us do that. So we'll say let previous node equal. Do we really even have to say previous node? Does it really make sense? We'll just say let previous equal null. So I'll be changing this to previous. Let me remove the node inside. Good. So now we have previous. Then we will now have another pointer, which will be next node. So I'll bring the next node here. Now the question is, what is the work of this next node? So I said earlier that this current dot next will have to turn and point to previous, right? Now we need to be able to remember where we are going next, or we need to be able to keep a track of the next node, the node that we want to move next, right? This next node, this pointer actually helps this current to know where to land next. That's just the work of this next node. So now that this current has turned it next to previous, it needs a pointer. We need a pointer that will be able to tell current, okay, you want to make a next move to so place. So this next node, keep track of that, right? So we'll be able to use this next node. Okay, current, since you've now your current.next has moved to previous, now current move to next node. So we need this pointer to be able to keep track of the next node to current, right? So we were going to say here, let next node equal null. We'll still initialize it to null. Good. So this is our first step on reversal. We'll do this 3. So let me return everything. So we'll now start from scratch, from head. We'll start moving everything. Good. So from here, current is already pointing to head, right? And previous is initialized to null. Next node to initialize to null. So now we want to traverse this list. So we're going to say while current is not equal to null, because I will explain. While current is not equal to null, what do we want to do? Now, this condition, what do I mean? For us to actually traverse a linked list and then carry out a reversal, there must be a node in the system. You get it? So if current, now that we've made current equal head, right? And then we find out that the linked list current is null. What does that mean? It means that the head is null. There's no node inside the linked list. And we literally can't do any reversal in an empty linked list. You get the point? So why current is not equal to null, this condition has to be met that current is not equal to null. There's a node. There must be a node inside the linked list. So why that happen? What do we want? We want next node, like I said, the work of this pointer is to be able to keep track of the node after current, because this helps current to know where it is heading to after it has carried the reversal of his pointer, right? So next node should be equal to current.next, right? So we'll say next node is equal to current.next, which is current node. So we'll say next node is equal current node dot next. So it's already sitting in that position, right? Now the next thing is our aim is to reverse this pointer, the current pointer. So we'll now say current node dot next, which is the pointer now, is equal to previous node. Just pay attention. This reversal is very, very interesting. Now, current node dot next is equal to previous node. So we put that current node dot next is equal previous. Equal previous. Now, we've already done that. Now that we've done this, we'll now say previous is equal current node. Previous moves to this point. And now you're going to understand why it will move here. It has to move here so that this current node will find its way to this position. And then the reverser will continue so long as there's node in the linked list. Right? So we'll now say previous is equal current node. Now, as this happened, current node will now make a move to the next node. So the cycle is complete. Now, so let's do that. We'll now say current node is equal to next node. Now we are done with everything that has to happen in the while loop, in the loop. So once this happens, this condition will not run again. I will not check, is current pointing to a node? If current is pointing to a node, yes, at this state now current is pointing to a node. Okay, we'll not say okay. Next node, move to current.next. Next node, move to current.next, equal current.next. Yes. Now the second one, we'll say current node.next is equal previous. This is equal previous. You see how the pointer is pointing, reversing one after the other. Then previous node equal current node. Previous node, or previous rather, at this state now, equal current node. And then current node, lastly, current node equal next node. And then this will continue again because current is pointing to a node. Current is not yet null. While current is not null, so this condition is not met. It's still met. Current is still pointing to a node. So next node, move to this current.next. The second line, current node.next equal previous. This equal previous. Then this previous equal current node, and current node equal next node. And then the condition check again. Is current equal null? No, current is not equal null. So we'll now move. Okay, current node, next node equal current node.next, which is this. At this state now, next node is started pointing to null. Now current node.next turns, become equal previous node. Previous node equal current node, and current node equal next node. Now we check again. The check goes on again. Is current equal null? This should be current node. Sorry, let me correct that. Yeah, sorry for that omission. So our code would have gotten error. So is current node equal null? Yes. When current node is not equal null, but this state now current node is equal null. So for the fact that this condition is not met, of course, you know how it works. This code is going to exit, right? Perfect. And now that it has exited, if you look at it now, you see that we have just successfully reversed the all the node nest, right? So at this state, what do we now do? We now say tail should be equal to head. Tail should be equal to head. So we'll now come here and say this dot tail is equal this dot head. And then we'll now bring our head and say our head is equal to previous node. Because at the end of the day now, if you look at it now, tail has left here. So there's no way we can reference this node. That's more reason why we have this piece. So at the end of the day, current node is off. Next node is off. We are now left the previous node pointing to the last node. So we need to be able to say, okay, head, this is where you should be pointing to. So we'll now say head is equal previous node. So head should point to previous node, which is now our new head, right? So we'll now say this dot head is equal previous node, is equal previous. Then what are we returning at this state? We are returning this linked list. We're returning this linked list, right? So this is the linked list. Remember, every of our code is inside this linked list. So we're returning this linked list. So we'll just say return this. So we'll say return this. And that is it for reversal. Let's test our code and see if it's working fine. So here we'll say console.log my linked list reverse. That's all. Okay, so we'll check. Perfect. So you can now see that head is pointing to 9 and tail is pointing to 2. So our code is working perfectly fine. And that's it for reversal. Thank you very much.